10, 9, 8. Just 10 seconds. Imagine for a moment that you're standing in a massive, sprawling industrial facility. The air is totally clear, everything seems completely normal, and you're just going about your day. Suddenly, a pipe ruptures. You don't see anything, you honestly might not even hear anything, but a countdown has just started. That terrifyingly brief window of time, just 10 seconds, is literally all that stands between a perfectly normal day and absolute catastrophe.
Yep, 10 seconds. That is exactly how long it takes for a high concentration of a very specific, totally invisible gas to cause a sudden, unavoidable fatality. It shuts down the nervous system, knocks out the respiratory drive, and basically ends a life before the person even realizes they're in danger. And the crazy thing is, this isn't science fiction. This is a daily, perfectly real occupational hazard in the global oil and gas industry.
Welcome to today's Explainer. We're diving into something pretty wild today. We're going to explore the fascinating official standards used to manage one of the most dangerous substances on Earth. We'll be uncovering exactly how world-class engineers design, build, and operate massive industrial fortresses that are specifically engineered to contain this invisible, highly lethal threat.
So, here is our survival guide for today. First up, we'll look at the invisible enemy itself. Second, designing the fortress. Third, mapping the danger zones. And finally, the human defense line. Let's get right into it. Section 1. The invisible enemy.
All right, so we are actually looking at a two-front war here. Hydrogen sulfide, or H₂S for short, is absolutely highly toxic to humans. At just 100 parts per million, it is immediately dangerous to life or health. But here's the really interesting part. It is severely corrosive to metals. H₂S doesn't just threaten the workers, it actively attacks and destroys the very steel trying to contain it. When H₂S mixes with water, the sulfur combines with iron, which frees up hydrogen. That hydrogen diffuses into the solid steel, collects at microscopic defects, and builds up so much internal pressure that it literally cracks the steel open right from the inside. They call this hydrogen-induced cracking. So this gas is basically constantly trying to break out of its own cage.
Section 2. Designing the fortress. Okay, so knowing that the enemy is invisible, lethal in 10 seconds, and actively eating away at your pipes, how do you even begin to safely process it? Well, you build an absolute engineering marvel. The outer walls of our fortress are built using highly specialized, anti-corrosive metallurgy dictated by really strict NACE standards to resist that stress cracking we just talked about. But building strong walls just isn't enough. You also want to make sure your people almost never have to go anywhere near those walls. Engineers achieve this through what's called minimum intervention design. Instead of an operator having to walk up to a dangerous pipe to read a gauge, we use remote transmitters. Instead of screwed pipe fittings, which can leak, the construction is primarily welded. And think about the sheer engineering involved here. Down inside the earth on any well producing more than 500 parts per million of H₂S, they install fail-safe downhole safety valves. If anything goes wrong on the surface, the well literally automatically chokes itself off deep underground. But hey, what happens if the primary containment actually fails? The moment outside sensors detect just 10 parts per million of H₂S, a temporary refuge building instantly transforms into an impenetrable safe haven. The HVAC air intakes automatically slam shut so they don't suck in any toxic air, magnetic doors engage to secure a double-door airlock, and this is brilliant. The building's internal systems generate a positive pressure of exactly 50 pascals. This means the air pressure inside the building is slightly higher than outside, so if there's a microscopic crack in a window seal somewhere, the air blows out, making it physically impossible for the toxic gas to creep in.
Section 3. Mapping the danger zones.
To manage this spatially, engineers divide the entire facility into 3 strict zones based on toxic dispersion modeling. First up, the yellow zone. Out here, a release could be lethal over a prolonged period. You're safe enough that your emergency escape breathing apparatus, or EBA, just needs to be at a strategic location nearby, usually within about 15 meters. Take a step closer, though, and you enter the amber zone. Here, a release could be rapidly lethal. You no longer have the luxury of running 15 meters. Your escape mask absolutely must be physically carried on your person or kept within an arm's reach. And finally, we step into the red zone.
Let's really contrast these two inner zones to understand the gravity of this. Over in the amber zone, the math calculates that if a leak happens, you've got roughly 45 seconds to grab that mask off your hip, throw it over your face, and start breathing safe air. But in the red zone, you are essentially walking into the villain's lair. It might be a highly congested space or a valve pit. The math here is genuinely terrifying. You have zero time, literally none.
If a leak happens, you will be overcome immediately. Therefore, you can't just carry a mask. To even cross the threshold into a red zone, you must already be wearing an active, self-contained breathing apparatus. You have to be fully armored up, breathing bottled air before you even open the door.
This kind of spatial mapping dictates an automated, split-second technological defense line. Because, let's face it, humans are simply way too slow to react to an invisible, zero-second threat. So the facility uses continuous optical and electrochemical sensors mapped out in a specific grid. At 10 parts per million, warning alarms sound, and those safe haven HVACs shut down. At 15 parts per million, the immediate evacuation alarm triggers, with high-pitched tones and flashing blue beacons cutting right through the industrial noise. But if 500 parts per million is detected, which is a massive, highly lethal release, the facility's emergency shutdown valves instantly activate. They automatically isolate and chop those massive pipelines into smaller sections, locking the gas inside before a human operator even has time to reach for a radio.
Section 4. The Human Defense Line. So, we've seen the incredible metallurgy, the positive pressure refuges, and the automated shutdown systems, but here is a hard truth about industrial safety. All the sensors and steel in the world are entirely useless without the right human culture. The crucial point here is that your ultimate armor isn't actually your personal protective equipment, it's the operational protocol. Literally nobody just wanders into an H₂S facility. Everyone undergoes mandatory competency certification. There is strict access control and tracking, so command knows exactly who is in a hot zone if things go south. Every single task requires a rigorous job safety analysis and a formal permit to work. And perhaps most importantly, the buddy system. When you go into a red or amber zone, you never, ever face the invisible threat alone. Your buddy is there specifically to remain alert, monitor the air, keep rescue lines clear, and ensure that if the unthinkable happens, you are pulled to safety.
This all culminates in a really powerful cultural philosophy. I am the difference. We will always find the time to do it safely or not do it at all. And that isn't just some empty corporate slogan. In an environment where a single mistake can cost a life in 10 seconds, this 100% health, safety, and environment philosophy empowers every single worker on the ground. It gives the absolute newest technician the ultimate authority to stop a multi-million-dollar operation dead in its tracks if something doesn't feel right.
We'h explored the NACE standard steel, the 50 Pascal pressure rooms, those split-second automated valves, and the strict human protocols that make working around hydrogen sulfide possible. It is a stunning balancing act between cutting-edge industrial engineering and unyielding human discipline. Which leaves us with a really fascinating question to ponder. When we extract the dangerous energy required to power our modern world, is the ultimate safety mechanism the machine that contains the threat, or the focused human mind that respects it? Really makes you think, doesn't it? Thank you so much for joining me for this explainer, and keep asking the big questions.